Okay, let's go a bit further with these reversible reactions. When we talk about equilibrium, then we mean the state of conditions, the set of conditions that reach a point where there's no overall change in the amount of the left-hand side or the right-hand side of the reversible reaction. Okay, to explain how we get to equilibrium, we need to imagine that our reactants are in a closed system. In other words, nothing can get in and nothing can get out. So if you look at these steps here to explain how equilibrium is reached, in step 1, A and B are becoming, A and B are reacting at the start. The chance of them colliding is greatest. The rate is at its maximum for A and B reacting. As A and B react and start to produce C and D, then the chance of A and B colliding is still greater than C and D, but C and D start to react. Okay, C and D are now getting in the way, collisions are becoming less frequent, but C and D are also reacting, and eventually you can see that as the rate of the reaction between A and B decreases, the rate of reaction between C and D increases as the amount of C and D builds up, until we get to a point where the rate of reaction of A reacting with B is the same as the rate of C reacting with D. And if we looked at that on a graph, we would see that it looks like this. So you can see in the red line here, the forwards reaction, A reacting with B, starts off at its maximum rate. The rate slows down, and the reaction in reverse of C reacting with D increases, greatest chance at the start, like all chemical reactions, but both lines eventually come to a point where they are at an equal rate. Okay, and we say that this is equilibrium. Higher tier students, you need to understand that Le Chatelier, scientist, made lots of experiments to do with reversible reactions and the position of equilibrium. And there's a straightforward rule to get your head round that when you have a closed system and equilibrium is reached, if you change something, then the position of the equilibrium will alter to try to cancel out the effect of the change. So in a closed system, imagine you could change something about that system, and that would mean that the equilibrium point would also move either towards the right, the forwards reaction, or towards the left, the reverse reaction. In this example here, iodine monochloride, which is brown, reacts with chlorine reversibly to make iodine trichloride, which is a yellow solid. Okay, if you add chlorine gas, so there's plenty of it, then the reaction will move forwards and you would see yellow crystals. If you took the chlorine away, then the iodine trichloride will break down into iodine monochloride and you would see a brown liquid. So often in a reversible reaction, especially on exam questions, there will be something to say you would see. In this case, if the forward reaction is happening faster, you would see yellow crystals, and if the reverse reaction is happening faster, you would see brown liquid.